We take the air we breathe for granted, but floating within it is an invisible battlefield of pollutants, pollen, bacteria, and microscopic dust. To clear the air, engineers created the HEPA filter, short for high-efficiency particulate air. A standard HEPA filter must trap at least 99.97% of particles as small as 0.3 microns. To put that in perspective, a single human hair is about 70 microns wide. We're talking about capturing objects 200 times smaller than a hair's width. This isn't just a screen or a sieve, it is a masterpiece of fluid dynamics and material science. If it were a simple mesh, it would either clog instantly or let the smallest particles sail right through. Instead, the HEPA filter uses a chaotic forest of glass fibers to achieve the impossible. In this deep dive, we are stripping back the outer casing to reveal the physics, the chemistry, and the brutal manufacturing process that turns raw glass into the ultimate shield for our lungs. From clean rooms to massive industrial ovens, this is how a HEPA filter is built. It all begins with fire and sand. The heart of a HEPA filter is made of borosilicate glass fibers, a material chosen for its incredible strength and chemical resistance. In a massive industrial furnace, raw silica is mixed with boron trioxide and heated to temperatures exceeding 2300 degrees Fahrenheit. That is hotter than flowing lava. Once the glass reaches a molten state, it is forced through tiny nozzles called spinnerets. Imagine a high-tech cotton candy machine. As the liquid glass is spun out, high-speed jets of air blast the strands, stretching them into fibers of varying diameters, some as thick as 5 microns, others as thin as 0.5 microns. This variation is critical. Unlike a uniform mesh, a HEPA filter needs a disorganized structure to trap particles effectively. These fibers are cooled instantly as they fly through the air, solidifying into a delicate wool-like mass. This raw material, known as glass wool, is the foundation of the filtration medium. Every single fiber must be flawless, because a single break could create a microscopic bypass, ruining the filter's efficiency. The glass wool is now transported to a wet lathe processing line, a system very similar to traditional papermaking, but with far higher precision. The fibers are dumped into a massive vat of water and chemical binders, creating a thick slurry. This mixture is agitated to ensure the fibers are perfectly randomized. Then, the slurry is poured onto a moving mesh conveyor belt. As the water drains away through the mesh, the fibers begin to interlock, forming a thin, wet mat. This mat passes through a series of heated rollers that compress and dry the material, bonding the fibers together into a dense, non-woven fabric. This is HEPA media. It looks like thick white paper, but under a microscope, it is a dense, three-dimensional labyrinth. The spacing between the fibers is actually much larger than the particles they are meant to etch. It seems counterintuitive, but the physics of how it works is far more complex than a simple net. The thickness of this media must be controlled to within microns, ensuring the perfect balance between air permeability and particle capture. How does a fiber web catch a particle smaller than the gaps between the fibers? It uses 3 distinct physical principles. First is interception. This occurs when a particle follows the slipstream of air and comes within 1 particle radius of a fiber. It simply touches the fiber and sticks due to van der Waals forces. Second is impaction. Larger particles are too heavy to follow the sudden curves of the air around a fiber. Their inertia carries them straight into the fiber where they are trapped. But the real magic happens with the smallest particles, those below 0.1 microns. These aren't just blown by the wind, they are bombarded by air molecules, causing them to move in a zigzag pattern called Brownian motion. This chaotic movement, diffusion, virtually guarantees that the smallest particles will eventually strike a fiber. This is why HEPA filters are paradoxically more efficient at the smallest scales. The most difficult particles to catch are actually the middle-sized ones, around 0.3 microns, which is why that specific size is used to rate a filter's efficiency. A flat sheet of HEPA media is remarkably efficient, but it would clog in minutes if it were used as is. To increase the lifespan and airflow, the media must be pleated. This is done by a high-speed mechanical pleater. The sheet is fed into a machine that uses precision blades to fold the paper into a zigzag pattern. This pleating increases the surface area over 50 times compared to a flat sheet. It is like taking a football field-sized blanket and folding it down to fit inside a suitcase. This massive surface area means the air moves through the media at a very low velocity, giving the physical mechanisms of diffusion and interception more time to work. As the paper is folded, tiny ribbons of hot melt glue, or separators, are applied between the folds. These separators ensure the pleats stay open and don't collapse under the pressure of the passing air. The geometry must be perfect. If the pleats touch, the dead spots reduce the filter's effectiveness and increase the energy needed to push air through. Even the best filter media is useless if air can leak around the edges. This is why the seal is the most critical part of the assembly. The pleated filter pack is placed into a rigid frame, usually made of extruded aluminum, galvanized steel, or high-impact plastic. But simply sliding it in isn't enough. A specialized two-part polyurethane sealant is injected into the channels of the frame. This liquid resin flows into every microscopic gap between the filter media and the frame wall. As the resin cures, it creates an airtight, leak-proof bond. For high-end industrial filters, a secondary gel seal might be used, a soft, jelly-like substance that creates a vacuum-tight fit when the filter is pressed into its housing. This ensures that 100% of the air is forced through the glass fiber labyrinth. There is zero tolerance for error here. A single gap the size of a pinhole could allow thousands of particles to bypass the system, compromising a clean room or a hospital surgical suite. Before a HEPA filter leaves the factory, it must prove its worth. Every single filter is subjected to a rigorous leak test, often using polyalpha-olefin or PAO oil. This oil is aerosolized into a mist of particles exactly 0.3 microns in size, the most penetrating particle size. This mist is blown into the upstream side of the filter at its rated airflow. On the downstream side, a technician uses a specialized probe, a light-scattering photometer, to scan the entire surface of the filter. If even a tiny spike in particle count is detected, the filter is rejected. They also measure the pressure drop. This is a test of how much force it takes to push air through the filter. If the resistance is too high, the filter will strain the HVAC motors and waste energy. Only when the filter achieves its rated 99.97% efficiency and the pressure drop is within spec does it receive its serialized certification. This is not a batch test. Every single HEPA filter is individually tested and documented. The finished HEPA filter is a testament to human engineering. What began as raw earth and fire has been transformed into a sophisticated physical trap. From the chaotic entanglement of borosilicate fibers to the precision-pleated geometry and the airtight seals, every component has a job. These filters are the unsung heroes of our modern world. They sit silently in the ceilings of microchip fabrication plants, preventing the smallest dust of dust from ruining a multi-million-dollar wafer. They operate in hospital isolation wards, trapping airborne viruses to keep healthcare workers safe. They even reside in high-end vacuum cleaners, ensuring the dust we pick up doesn't just blow back out the exhaust. By mastering the invisible physics of diffusion, impaction, and interception, we have built a barrier that keeps the microscopic world at bay. The HEPA filter, a simple-looking box that performs a complex miracle with every breath we take. This is the art of engineering the invisible. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.